Hey, it's Julia, and this is a visual Python model of Newton's Cradle that I made. So Newton's Cradle is an example of the conservation of kinetic energy and momentum. So in this model, the leftmost green ball, we can pick it up, and then it'll drop down, and they'll all collide, and then that'll send the rightmost red ball going up and down, and then the model can just keep running, so on and so forth. So let's first talk about the framework, which is set up here. So the first 5 lines describes the 5 balls, and it was really fun to mess around with materials because you can change them to a variety of different things. So that's why one of them is a marble and the other 4 are plastic. Next we have the 4 cylinders at the top illustrated here, which are these 4. Next we have 10 walls, which are in fact the 10 purple strings, and it's much easier to see if you rotate the model around, because from the front view it looks kind of funky. Okay, and now we have the 4 vertical cylinders. I don't know why they're called rods, I don't know. Okay, and they're here. Okay, now we can talk about the 2 simulations. So the first simulation is just for picking up the leftmost ball in a somewhat naturalistic way until it reaches a 14-degree angle. And this angle is just between like the ball and the y-axis. So first we have something called lift, which is just a variable that for an infinite series. So it starts at 1/2, then goes down to 1/4, 1/8, and so on and so forth until it reaches essentially 0. Now, unfortunately, it can't reach actually 0 because the program wouldn't stop running, and that's quite awkward to watch. So here, instead, we have the ball rotating with each turn of the while loop at at half the angle that it rotated at before until it reaches negative 0.244, which is 14 degrees in radians. Okay, so now we have the simulation for Newton's Cradle. So first, now at this point, the ball will have reached the 14 degrees and it'll start going down. And that's where this model begins to run. So let's define all of the variables first. So g is gravity, t is time, r is the length of the pendulum. So now, in this model, Newton's Cradle is modeled on a pendulum because, I mean, there's different ways to do it, because originally I was trying to write one using angular acceleration, velocity, and theta, but that wasn't working so well. And also, you can probably write a program based on the conservation of kinetic energy and momentum. Here, this program is just based on pendulums, because it looks like the leftmost ball and the rightmost ball are 2 halves of the same pendulum, and r, in this case, capital R, is the length of the pendulum. And it's easier to see if you move it here to this angle, that the length is effectively this region, because it's the same thing as having 2 strings that are on opposite sides. It's just one going down the center. So since this is 4.8 in terms of the y-axis coordinate, and this is 0.5, we have 4.3. Okay, let's move on. Theta is just the original negative 0.244, while neo theta right now is just 0, but that'll just be the updated theta as we start moving through the while loops. Delta theta is just the difference between nu theta and theta. Now we have the same for the rightmost side, so let's move it back to a front view. And finally, we have the period, which is 2 pi over the square root of gravity over the length of the pendulum. Okay, so now we can move on to the 3 while loops, and we can start running the program. So there it goes up, and second simulation. So this is Newton's Cradle running. So we can divide the period into 3 different segments. So the first segment goes from 0 to 1/4 of the period, and that's where the green ball is going down, as we just saw right there. And this can be modeled by a negative cosine function. And then we just set the variables, and this is the same for all of the other while loops, and the rotation. So it rotates by delta theta with each time increment, and then you just update the time, the thetas, and delta theta with each loop. And now we can move on to the second while loop, which goes from 1/4 of the period to 3/4 of the period. And this is when the red ball goes up, then it goes down again. And this can be modeled by a sine function that has a shift by 1/4 of the period. And then it's the same type of updating deal going on here, just with the right variables as opposed to the left ones. And for the final while loop, we have the period from 3/4 to 1 times the period. And that's just when the leftmost green ball goes up again, so from like that part. And this is just modeled by the original negative cosine function that we had right there. And same deal with updating. So this program runs forever because it's always true, I guess. Yeah, so it's pretty fun to watch, and that's the explanation.